Well, thank you for taking your time to see this presentation. And here in Göttingen, we focus more in disease control, in the generation of application maps. And this was the main topic of this demonstrator. As Lasse mentioned, introduced us, we focus more in using multispectral imaging taken by a drone. And yeah, well, in this presentation, we are going to cover 6 points. First, to understand the motivation of the demonstrator, we want to present you our field trials. And we will also give an overview about how the pipeline for analyzing the multispectral images works. Also, how we generate our disease maps, especially how we produce our disease incidence in disease severity maps. We're going to show you some preliminary results of last year and also some results of the ongoing experiment this year. And in this demonstrator, we also use as an automatized way to apply fungicide by taking as a platform also a drone, a sprayer drone. And we make also some experiments about how should it works if we have to apply in a specific area on the field. And for that topic was important to make some analysis, and we make some cooperations with some partners, and BASF helped us to make some leaf coverage analysis. And so we're gonna give an overview of the results also. Well, for sugar beet production, leaf disease is a big topic. There are many leaf diseases that are covering and are affecting the productivity in sugar beet production. Some of these are, for example, fungus, but we have also some viruses, especially yellow viruses. And from these funguses, from these fungus, we have one of the most common diseases are Cercospora leaf spot, body mildew, and also beet rot that commonly comes into the field. But from all these three diseases is one of the most damaging Cercospora leaf spot, which is actually caused by a fungus called Cercospora reticulosac. Well, the damage can cause including 40% of yield losses. This is a very strange pathogen, can I say. It's until now not 100% understood how it is spread into the field. Many theories say that it's an airway to spread through sporulation. Another theory say is the machinery that spread the diseases, is the water splash that spread the diseases. It's a combination of all of these aspects that support the spread of diseases, and all these aspects of the pathogen may really difficult to control, and it's already several years that Cercospora leaf spot is causing headaches for sugar beet growers, and is continuously a topic in the cultivation here. So to control and to start many programs in terms of breeding, but also in disease control, is require field assessment. And by now, it's all of them implemented manually. And so we train people which are expecting try to estimate the quantity of disease into the field. And they give us until now the decision making. This is very important, and this is a fact that is happening right now in the agriculture. And here at the IfZ, we also test the products for controlling the disease spreads, in this case, fungicides. And here's in the right side of our slide a list of 12 fungicide products that are commercially available right now, that in the past could control the spread of the disease, but right now in year 2022 are not having any more these efficiencies. So there is a continuously adaptation, evolution, or development of resistance of the fungus. And this is the main idea of the demonstrator, also to support and to reduce the risk of pathogen development resistance. How? By lower intensity of the fungicide application. In that way that we reduce the selection pressure of the pathogen. In that way that we also slow down the development of the resistance, and these fungicides are more available in a longer time for the growers. All of this is implemented in integrated pest management for leaf diseases, and this protocol is actually mostly created by studying how the pathogen spread into the field. And several years, many research groups, especially in the 90s and until 2012, they focus and how and to see into the field how the pathogen spreads. And they define 3 stages. The first stage is the so-called horizontal spread into the field. So the pathogen go from plant to plant very quick. Then is also defining a vertical spread. This means that the lesions of the pathogen start going from the lower leaves into the middle leaves. And finally is the necrotic tissue. So the leaf area is damaged, necrotized area comes, and therefore the yield penalty is available to see into the field. So the integrated pest management decide here to make a curative application. This means the pathogen is there, already there, but we have to take this decision before it goes to this second phase. And for this, we need to quantify the disease into the field. And one of the most common parameters is the so-called disease incidence for that. It's a way to standardize our indicators in order to go into the field and apply fungicide. So the objective of the demonstrator was to detect the disease into the field. Second, to develop the disease maps and application maps. And third, to see a way to apply in a site-specific way, manually or automatically, the fungicide. We have already a workflow, and my colleague also, Facundo Spisua, presents you this slide probably. And our workflow was with multispectral UAV systems. So we have a drone that try to fly really, really low, 6 meters high, in the way that we get multispectral images with a resolution of approximately 3 millimeters. This is a sensor that inspects 6 channels in the spectral wavelength. Yeah, 3 channels in the visual region, 2 channels in the near infrared region, 1 channel in the long wave region. Parallel to this, we go into the field and we quantify the disease. This is our reference data, and we try to establish these 2 parameters. No, as I mentioned before, disease incidence, the way how the pathogen spreads with high sensitivity, and disease severity when the pathogen start damaging the leaf area. During this research, we try to we published 2 models that actually were crucial. The first model was actually focusing on instant segmentation method, which focus in the segmentation of the object to quantify the disease. We publish this research is right now a preprint version, but will be published in the next one. This is in the last stages of revisions, and I invite you also to check this publication if you are interested in it. Well, the main idea was actually to segment the leaves, and the model have to be somehow deal with this disease factor. I mean, that the model have to segment leaves that are necrotic already, sometimes that they are brown, also very similar to the soil. They have a really strange form. You can see some crazy forms that can come when the pathogens start doing damages. They have to deal with active and passive illumination also, because we have to adapt. We have to adapt to requirements of the parameter. How it depends, and it is independent of the environmental conditions, because when you have to go to the field, you don't need to wait for it. And this was all these factors that we try to cover in these publications. A second model actually focus and take these segmented areas and classify each pixel in 4 classes: healthy tissue, diseased tissue, and the case also areas in the images that are belonging to the soil, and another X epsilon factor that can be also in another perspective from the imaging, from the drone imaging. Weeds, for example, in the field there is also some installations and any other object that can take and can affect the quantification of diseases. Yeah, this is also a model that can be transferred to semantic segmentation, but until now we didn't have the time to cover this area, this point. Well, the pipeline, as an overview, work like this. We go into the field, we overfly with really high resolution. We run our first model. Our first model focus and segmentate the scoring units, our leaves. But it's not the leaves. We also understand with the time that another instances form or another segmentation form can deliver another kind of parameters. I will go in the next slide into it. Second, when we have the instance, we go into the instance and we try to classify pixel-wise if the tissue is damaged or not. And secondly, we do some post-processing analysis, for example, clustering by connected points, and we try also to quantify these connected points, how many there is in the leaves, how big are they, and how are they spread. And all of these are parameters that can we extrapolate and deliver as a disease map. As mentioned before, it's possible to segment the images in different ways. My colleagues Facundo Piso and Maurice Kunde focus more on the segmentation via plant unit, which can deliver another kind of disease maps. But in this work, we see a lot of potential also by segmenting the leaves, especially by segmenting a circle weight. So the segmentation of the images in circles had the advantage that you can quantify the plant cover, for example, in different areas. The disease severity, which is the ratio of diseased classes with complete vegetation area. You can quantify if at least one diseased point between the instance is, detect this as a diseased unit, and then by a sampling, extrapolate as a disease incidence value. You can quantify the number of lesions also by clustering the diseased output, the diseased matrix. By having the segmented leaves, you can check by using the slope from digital surface model, the leaf inclination, for example, the leaf healthy area between the leaves, the total area of the leaves, the size of lesion in the leaves. So there are many possibilities to deliver a different way to estimate diseases into the field. Now I'm going to explain more about our experiment in 2022. This was a demonstrator. And in the demonstrator, we try to use 2 variants, site-specific variant that actually should be applied by using the disease maps, and a uniform variant that is actually a variant that uses the EPM, also the integrated management that right now the growers use into the field. By previous by previous experiments, we observed that we have to establish from our disease incidence calculated from multispectral images our own thresholds. And we try to plot different disease incidence curves. And one aspect that we observe is that many parameters have to be controlled. For example, if you define a diseased unit and you make a definition, for example, okay, quantify this instance as disease if you find a number of cluster, one number of cluster, then we observe that our false positive classification delivers inaccurate disease maps. But we can control this if we say to our disease, to our algorithm, okay, quantify this instance as diseased if you, for example, have 3 clusters or 5 clusters of 6 clusters, which can be correlated to 5 or 6 spots. In that way, we observe that we reduce our false positive rates. We can get a more accurate curve into the leaves, but we have a delay in the time of the disease incidence development, which are one of the disadvantages that can be by reducing the false positive rate with our states of our pipeline. So we focus that okay, maybe one point to establish as an indicator or as a threshold should be to put this 25% of as disease incidence to apply fungicide. I mean, when we detect this into the field, we will segment the area and we will go into the field in at least in 2022, apply manually. We have 2 specific application systems. In 2022, we apply manually. And in 2023, we use an automatic way, this time in aerial vehicle, a drone for my design-specific applications. We will observe some results of using the first systems and also some analysis of this second platform. Here is some explanation how is the dynamic and the spread of the disease maps. Here's a parameter, the so-called disease severity, which quantified areas of diseased tissue between the leaves, for example. And you can see that, for example, last year in August was very low disease severity, almost 0 in the complete field. However, if you go into a parameter that is more sensible, like the incidence, you can start seeing the spread of the diseases. In these red points were points where we artificially release the disease, we inoculate the disease, and this way to analyze or to quantify the disease can deliver you a more sensible weight and can, by establish threshold, for example. This is a presentation how with high resolution they looks like and the quantity of the disease incidence in every region. And if you establish one threshold, it's possible to make 2 classes and define the areas that you have to go and apply manually. This is actually the way and the logic how the application maps works. And this is a presentation also for another possibilities. For example, this is a quantification of the disease maps of the parameter disease severity first by using the instances of leaves. You can see there is a high intensity in the inoculations points, but disease incidence, as I mentioned before, is a parameter that's more sensible. The values are higher. You can take more sensitive decision making, and this is the main parameter for applying fungicide for a specific application. But you can also make a time series evaluation to make, for example, yield analysis. And this is information that you can also use with the disease maps. Here's an overview from the year 2022, how our application schedule works. On the right side of this timeline is the uniform application that we actually use for, we apply with a normal tractor, extensive, and we use the thresholds that establish the IPM in Germany. And we see that in totally we apply one in one date, and the main definition is we make an application a bit late, because when you quantify a parameter in a big field, you can find by chance or not the location where the disease is accumulated. This is one advantage that we see when we make a georeferencing disease quantification. We can detect these spots and take individual decisions, and therefore maybe an early decision making. However, one of this is a development of the site-specific disease quantification in the applications maps. We observe also that when we fly it and then we apply it take us one delay, a processing delay. It was an offline system. By now is one of the points that we need still to optimize, reduce the processing time. It took us these high resolutions orthomosaic maps to classify approximately two days, and this is something that we have to reduce because this delay of time for the decision making is crucial. We can also observe that this site-specific application, there is another agronomical factors, like for example waited time from a first to the second application. This is that, for example, we apply and at the middle of July, and then we again make a disease quantification less than 3 weeks, and according to regulations in Germany, you cannot apply it in two time periods 2 times. You need a specific time of waiting, in the way that the effect of the first application is probably still there. So therefore, there's another factor, waiting time for the following applications. Third factor is, the next threshold. We establish just one threshold value for the following application. We didn't know how to apply this second, or where to apply the second application, in which threshold. We just, in this ongoing experiment, focus in one threshold, and we observe that disease incidence goes down, but then later on it comes again into the same threshold value, and this, by our protocol at that 2022, says, okay, we have to establish a second application. We will see the consequences of this protocol, but this is an overview how can be the dynamic for site-specific application. We make a variance analysis of our field. We consider in the modeling 2 factors. The first factor is the strategy of the fungicide management. The second factor was the distance of the inoculation spot at the hotspot to the mini plot. And we observed that the yield values are not significant, whether by the site-specific application or by the uniform application, which is actually good. We observed that by using the parameters calculated with the instance in a circle form, and there are some significance, especially in the strategy of fungicide application, and especially by quantifying the area of healthy foliage. we observed that maybe because we apply more site specifically, uh, maybe because we make second application in site specific management, we keep our canopy healthier, but in this way it was not significant for the year, for example. We observe also that by making the segmentation with leaf units, some parameters are really correlated to the distance to the hotspot, and these are especially as we expected. This is instance calculated by leaf units, but also the number of cluster or the number of spot between instances, and this is also quite important maybe to consider in the future as an indicator for site-specific management. We can also see that, and this is interesting, this is maybe relevant to mention that there is two kind of disease severities calculated. The one is calculated in a circle form, and the second one calculated between the leaves. And this one is not significant, but if you start to make this quantification between the leaves, you start to be insignificant to the distance of the inoculation point. So the way how you segment your images is quite important for quantifying the disease. Somehow another important parameter for us was to consider the year and to see the correlations of the year, and we observed that in that way the most relevant instance was the circle form to quantify the leaves, and especially these parameters that are quite similar, which is the foliage cover, the cover of healthy tissue, the cover of the area of healthy tissue. We also calculate area with the surface model, and the disease severity is also important, but more interesting is that the circle wave is more important and correlated to the year in comparison to the leaf segmentation. We extrapolate. I mean, we make some samples of some areas, some grids into the field, and then we interpolate a yield map, and we can georeference it, see that there is a high correlation of these top parameters over the time, and we try to visualize our yield map also, and yeah, this is telling you that heterogeneity also into the field is one important factor for the yield, not just the disease spread. This correlation is also independent of the fungicide management, if this is site-specific or uniform actually. But here and we observed some disadvantage to our protocol, because we actually apply second time fungicide, and with this second application we debalance our consume of fungicide. So we apply more in the site specific at the end, but this realized that the thresholds and combination of different thresholds should be established in the future for a more accurate protocol of fungicide management. This is actually what we propose for the year 2023 by learning about the results of 2022. And we establish a new protocol in the way that we increase the number of clusters between an instance, we reduce our false positive rates, and we establish two new threshold values for a following fungicide application. We applied this new protocol in this year 2023, and we are looking forward for the year results, because the experiment is still on the field. But actually we made some modifications, some complementations, and in that way we use for the site-specific application the sprayer drone, and we have a cooperation also because of this experience with the BSF, because they they use the same system for applying their experiment, and we try to learn more about how to deal with this system. And this new experiment, we had 3 management strategy. One strategy was untreated with fungicide. The other one was with the standard protocol or the APM. And the third variant of fungicide strategy was the one controlled by the drone. Well, this is a present. Oh, hopefully I can run this. Yeah. Well, this is a way how the drone apply into the field. You can see that when the drone found the spot, it's started to create some turbulence into the field, into the canopy. Leaves are shaking. And this was one question when we were starting this experiment this year. Is this positive or negative in the coverage of the fungicide into the canopy? How deep goes the fungicide in the stages of the leaves? We didn't know. Actually, some theory was that turbulence is pressure in the canopy, and therefore the fungicide don't penetrate into the canopy that much, which will be negative. The other is that this turbulence is shaking the leaves and making a positive effect into the penetration of the fungicide in the leaf area. So therefore we found this cooperation with the BSF so crucial, because we made some tests about the application with the drone. And for this we make a sample of 2 points in a polygon that we apply with the drone, one in the center of the polygon and the other in the border. Parallel to this, we apply the same area with the tractor, and we try to see some differences. We make a sample in 2 levels of the canopy, middle leaves and all leaves that are laying almost in the soil. And then we try to make a leaf coverage test. And here we have some results. First, a presentation how it looks like, the analysis of the coverage of the application. We're trying to quantify how much fluorescence in the area is, and with this we observe that middle leaves are almost in the same coverage by the fungicide, by the drone, as well as by the tractor. But when we observe in the all leaves stages of the canopy, that the drone had some advantages. So the application, or this turbulence of the application with the drones, is positively affected the application of the fungicide, which was quite good for the use of drones in application. And nevertheless, this system have their own fly emission weight, and probably is standardized for many crops, but each canopy is different, and we observed that the polygon for our fly emission had some disadvantages in the border. We observed that the coverage of the fungicide was good in the center, but only 7% of this 100% was covered at the border, 20 centimeters from the edge of the polygon, which we realized actually too late, because the flight mission were already established in the time. We didn't wanted to move our protocol. These are information that we actually get 1 week before, and the results were, as you can see here, this is the near channel of the experiment, and here is our repetition, 1 repetition with the drone and 1 repetition with the tractor. And I don't know if you realize here some lines. White is leaves or canopies less stressed, red is more stressed. And yeah, we can observe that there is more damages in the borders of the polygon, and the canopy still is as good as the uniform application. So probably when we are flying with the drone or when we are applying site-specific application is the topic buffer areas really crucial. And this is something that we have to see for the next years. What are our future perspectives? So we have to find more accurate links or more accurate indicators for established application maps, especially what are the equivalents between UAV-based disease incidents and the expert-based, in the way that our indicators are more robust. And maybe in that way we will need a next level of ground truth. We are trying to establish a protocol of making sampling of leaps into the field and see if the disease already is there, or maybe how less sensitive is the drone for detecting a diseased unit or not. These are aspects that we have still to cover in a more detailed way. We need to optimize our algorithms in a way to reduce this processing delay. Maybe parallelism of work is still needed for the next month. We need to establish accurate buffer zones for a site-specific application, and this is important. And finally, we need to make a similar transfer or a similar disease quantification for another diseases, maybe also not just for leaf diseases, but also for soil-borne diseases. Well, in summary, we performed disease quantification. We developed of the determination of disease incidence by using UAVs. We understand a bit more how relevant are the segmentation of the orthomosaics by quantifying disease intensity. We could control the false positive rate by segmenting the leaves. The post-processing allow us to deliver more different kind of disease maps to quantify the disease in different ways. This allow us to make a decision making and establish indicators for a geo-referenced application. Yield is actually correlated more with the AUDPC and the leaves coverage. And drone sprayed presented a high leaf coverage in comparison to the tractor or the traditional application. However, buffer zones can be more accurate in the future. And well, with this, I want to finish my presentation, and I want also to thank to PhenoRob, but also the other additional partners that giving us and complement this analysis, such as BSF or Pharma Space, and of course our colleagues in the IfZ. Yeah, thank you.